Hello, everyone. Today we have this session in the machine learning theory channel of the Cohere Labs community, and the title is Large Language Models as Markov Chains. We have it with Ambroise Odonnat, and let me tell you a little bit about Ambroise. He's a PhD student at what we know as ARC Lab in India, advised by Romain Thévenard, Laetitia Chappell, and Evgen Redko. His goal is to improve the core understanding of transformers by conducting theoretical analysis and large-scale experiments on large language models, transformers fine-tuning, and out-of-distribution generalization. So these topics are very well aligned with our interests in our machine learning theory channel, so it's natural that we invited him for a talk. So without anything else to say, you can start.
Yeah, so hi everyone. Yes, thank you a lot, and I also thanks Ambroise, who couldn't come here, and the entire Cohere Labs and the ML theory group for inviting me. I'm very excited. So I will be speaking about the connection between large language models and Markov chains. So most of this talk is based on recent work with my co-authors, Oussama, who's a PhD student in Paris, Abdel, who's a PhD student in my lab, Linus, who's now a postdoc at EPFL, Nicolas, who's an assistant professor at Imperial, and my PhD supervisor, Yevgen, who's a research scientist at Huawei. So here is the outline. I will give some brief basic notions on large language models and Markov chains before digging into the main subject, the equivalence between LLMs and Markov chains, before speaking about what we can do from the theoretical and the experimental side with this equivalence. So yeah, don't hesitate to tell me if things aren't clear, and we will also have some time at the end of the presentation for questions. So yeah, to start with, so have you, I guess you're all aware of, we've seen in the recent years, and it's been increasing in the recent months, increasing and quite surprising capabilities of large language models, mostly from the generalization aspect, whereas they can have really good results, both in natural language and also in other kind of data like time series or dynamical systems, without having been trained on the same distributions. So this is so-called emerging capabilities or generalization capabilities. This is a phenomenon that is well observed in practice, and people have worked a lot to derive improvement, methodological improvement for the pre-training or fine-tuning or reasoning aspects to improve those capabilities. However, in the literature, we still lack some theoretical understanding of those generalization because it departs a lot from the more classical statistical learning theory. And actually, this will be the objective of this work and of this talk, is to derive some theoretical insights to better understand the generalization capabilities of large language models. So to start with, some background on autoregressive language modeling. I'm all sure you're aware of that. So we will focus in this talk, again, on autoregressive LLM, and in particular on transformer-based models, which makes for the large part of the state-of-the-art and open source models. So in the autoregressive framework, the idea is to predict the next token based on the previous one. So such that each token depends on some context and the past token. So if I take the sentence, "I am the danger," you could say that the context which will be fed your LLM is "I am the," and danger is the token to be predicted. So here in this example, and for the entire talk, I will assume that tokens are equivalent to words, although it's not the case in practice, it's just for the sake of simplicity. So what it means in terms of modelization is that if you have a sequence, the probability of having this sequence or this sentence can be decomposed as the product of the conditional probabilities. And this is exactly what motivates the autoregressive framework, where you only feed the context that is moving to predict the next token. So as I said, most of the state-of-the-art models rely on the transformer architecture, which was introduced in 2017. So here you have the famous and classical architecture, which is encoder-decoder, like the first LLMs, but nowadays it's more common to have only decoder-only architecture. So if you take your favorite LLM, whether it comes from Anthropic, Cohere, Google, Meta, Mistral, or OpenAI, or even other actors like Qwen and so on, it will be characterized by some vocabulary size, which is the number of tokens that will be used to encode natural language sentences, a context window, which defines the maximal size of a sequence that can be fed at once inside of your LLM. And of course, you have the neural network's parameters set. So for instance, for GPT-3, you have around 50,000 tokens, context window of 2,000, and more than 175 billion of parameters. And this is not a typo. It might seem surprising for people coming from the machine learning community and not deep learning, but in recent years, you have a huge increase in scaling in the model size, and the biggest models are even way bigger than that. So this makes it very, very hard to analyze, to understand, and this is why you have a lot of work both from the theory and also the interpretation side. So I mentioned the context window. This will be very, very important in the talk and also in the proofs for the ones that are interested in the paper. So as I said, you have a context window that defines the maximal size a sequence can be fed at once to your LLM. So if you have a sentence, a sequence of tokens, let's say here you have 4 tokens and a context window of 7, it can be fed at once without any problem, and you can just pad the remaining tokens for your LLM. But in the autoregressive fashion, when you are predicting the next token and you append it at the beginning of your sequence, at some point, you will have sentences that are bigger than the context window. So what is done in practice is that you have a so-called deletion process, where you just remove the first token such that you maintain a sentence of sequences equal to the context window after some steps. So you have a more thinner way to have a deletion process, but this is the global idea. The idea is just that at some point, the sequences will have a fixed size or smaller than the context window. And this will be very, very important to be able to do the equivalence between LLM and Markov chain. Speaking of Markov chains, again, I'm sure you're all aware of that. We will focus on discrete finite state space Markov chain. So you need a probabilistic space to define your Markov chain, and it's simply a sequence of random variables that takes their values into your state space. And you have the following property: the next observation is independent of the past given the present. So to explain what this means in terms of math, this is the so-called Markov property. It means that the probability of the next observation, so here xn plus 1, given the entire past, xn up to x1, is exactly equal to the probability of the next observation given the present, xn. And so here, the probability of going from xn to xn plus 1 is what we call a transition probability, because you'll transition between a given state to another one. And all those transition probabilities are gathered into a so-called transition matrix, which is simply a square matrix of size, the number of states. So now, after these very basic notions, we have one first and quite important question: are LLMs really Markov chains? So let's say we place ourselves at a natural state space that is at the token level. So each state is a token. It's quite natural because we are working with tokens and sequences of tokens and LLMs. So it means that the random variables take their value in the vocabulary space, and we wonder whether the Markov chain property holds or not. So again, if I take my example of the simple sentence, I am the danger, here again, each word is a token. So the question is, do I have the Markov property for this sentence where the past is I am the, and the next observation is danger? So the question is, do I have the equality between the probability of danger knowing that the past is I am the, and the probability of danger knowing only the present observation, which is the. And it's quite simple. If I change the context, and instead of having I am the, I have cheese is the question is, do I still have the same probability? And what you're all aware of is that cheese is very good and it's not a danger. You've changed the semantic of your sentence, so you've changed the probabilities. And in such case, the Markov chain property does not hold. So it's quite a bad news for me, because then it means that Markov chain, that LLMs are not Markov chains. But actually, it's simply because we did not consider the good state space. Let's say that instead of placing ourselves at the level of tokens, we place ourselves at the level of sequences of tokens. So now the transition probabilities are between the sentence I am the and the sentence I am the danger. And the question is, do we have the Markov property? So now we dig into the main part of the work. So I hope that the answer, the answer is yes, otherwise I wouldn't be here. So as I said, we place ourselves with the state space of sequences of tokens. And more precisely, I recall that your LLM have a specific number of tokens, the vocabulary size, and the context window. And I consider the set of sequences of at most k tokens. And you may wonder what it represents. Actually, if you remember what the context window is, it's the maximal size of sequences that can be fed at once to your LLM. So the states I consider is the set of the entire sequences that can be fed at once by my large language model. And once I have that, well, we have a Markov chain. So just before that, to realize what this space represents, you can see that this is a gigantic space. More precisely, you see that the cardinality of this space is exponential with the vocabulary size and the context window. So in the case of GPT-3, it means that you have, as number of states, 50,000 to the power 2,000. It's absolutely gigantic. It's way more than the number of atoms in the universe. You simply cannot compute it. But it's finite. And this is very important for us because, again, we place ourselves with discrete finite state space Markov chains. So now, how do I show that I have an equivalence between my autoregressive LLM and a finite Markov chain? So we have the state space, and what we need is to define the probability of going from one state to another. It will be encapsulated into a transition matrix, again, which here will be of size, the number of states. So it's gigantic. But what we simply need to do is to characterize the transition between the states. Here, again, the states are sequences of tokens. So we have a first scenario. We have two sequences of tokens that are not compatible. What I mean by that is that in the autoregressive fashion, in the autoregressive framework, my LLM is fed a sequence and it predicts a token such that the predicted sequence is a completion of the previous one. What I mean by compatible is that the two sequences I consider, the two states I consider, can be a completion of one another. So in the first case where it's not compatible, let's say that I have the sequence I am the, and I have the sequence he is a dog, I see that he is a dog cannot be a completion of I am the simply because the context is not the same. So in this case, my LLM can never transition from I am the to he is a dog. So I simply say that the probability of transitioning from I am the to he is a dog is 0. I simply cannot do it. Now, let's assume that I have compatible sequences. For instance, I am the and I am the dog. I see that the I am the dog is indeed a plausible completion of I am the. So what is the probability of going from I am the to I am the dog? Well, naturally, it's the probability predicted by my LLM that the next token is dog. And then I have my characterization. So as you can see, it's naive, natural, very simple. But we will see later that it is really, really useful as a point of view to derive theoretical insights on LLM. So once I have that, one simple remark is that this transition matrix is very sparse. I have very, very few non-zero elements in proportion with the size of this transition matrix, simply because most of the sequences that can be formed are incompatible. You don't have that much compatible sequence that are the completion of one another. And in particular, we can compute the number, or at least the proportion of non-zero element in this transition matrix, and it's proportionate to 1 divided by t to the power k. So again, you really have few non-zero elements in terms of proportion. But since the size of this matrix is gigantic, it's still a lot of entries to compute. Okay, so now we're very happy. We've done our work. We have a proper equivalence between large language models and Markov chains. But the question is, what for? As I said, the number of states is gigantic. You simply cannot store it, at least not with our modern computer. So you may think that it's quite useless. Actually, you can do some stuff. If you have access to model weights with a good open source model and few GPUs, what you can do is to access a row of this matrix, because again, as I said, to know how the probability of transitioning from one sequence of tokens to another, you simply need to recover the next token probability predicted by your LLM. So okay, it might be useful, but most of it is that we can use the very rich literature on Markov chain to derive theoretical insights on the generalization and on the dynamics of LLMs. And this is exactly what we will do in a couple of slides. So just a very simple example of what we can do with this equivalence if we had access to the transition matrix. Let's consider a baby GPT-2 with binary vocabulary, 0 and 1, and 10,000 parameters. So here we consider a context window of 3, which means that the total number of states, here the states are sequences of tokens of at most 3 tokens, is 14. So you have 0, 1, 0, 0, 0, 1, etc., etc. And now you can either use your LLM to predict sequences, the next token prediction, or you can use the transition matrix. So I don't dig into too much detail, but let's say that the input is a sequence of 3 tokens, 0, 1, 0. You can only take the 3 ones because the context window is 3. So you just have a probability vector that is just one hot encoding on the size, the vocabulary size, number of states, here 14. And you just need to multiply by your transition matrix to obtain the probability of next token. And then once you have that, you simply sample the most probable one, which here is the sequence 1, 0, 0, which means that the next token is simply 0, and you've obtained your completion. So it's nice, but in practice, you cannot store the matrix, but we will see that still we're not doomed, that we can do some stuff empirical. So just for the theoretical side, we've shown that we have an equivalence between large language models and finite state space Markov chains. And actually what we show in the paper is that we have the existence and unicity of this Markov chain stationary distribution. So in terms of LLM, what it represents is the long-term equilibrium of your LLM. Once you've reached this stationary distribution, you kind of fall into a deterministic model which will loop. And what's interesting is that this phenomenon has been observed in practice. People have seen that in some scenarios, you have a lot of repetitions and it forces people to impose some repetition penalty. Another thing that we've observed is that we have some bias towards the sequences seen during training, which makes sense, again, theoretically speaking, because the probability, if you're considering the stationary distribution pi and the states x sequence seen, the entry corresponding to this sequence is actually the average number of visits of these states by your LLM. So during the training, your LLM is seeing a lot of those training sequences, makes sense. So in the outputs, you have a bias towards these sequences because on average, you've seen them more than other sequences. So again, it's not really actionable because you cannot store the transition matrix, but conceptually, it means that if you manage to do that, you might have access to some training data. So it's connected to safety issues with LLMs. What we've also done in the paper is to characterize how fast you converge to this stationary distribution. So again, this is not a good thing because it means that if you reach it, you're kind of doomed and the prompts will not play a big role into what your LLM is predicting. And we've computed how fast this convergence is depending on the context window. So here, I don't dig again into too much detail, but what we show is that we've demonstrated, is that the bigger the context window K, the slower the convergence is. And when we take values from our toy baby GPT-2 and real models, we indeed see that we have a slower and slower convergence to the stationary distribution. So we're further from this bad scenario. It's actually a good thing, and what we've observed in the recent years and even the recent months is that the context window of state-of-the-art LLMs are increasing. Now we can almost feed books inside of this context. So it's a good thing because the more tokens you have, the less chances you have to fall into these loops of repetitions. Another thing that we've characterized is the impact of the temperature during the sampling on how fast you converge to the stationary. And actually what we've shown is that when you increase your temperature, you converge to the stationary distribution faster and faster. And again, it's connected to what people have observed empirically, is that when you increase the temperature, you decrease the coherence of the outputs. And again, it makes sense because once you've reached your stationary distribution, you don't have much choice, and your LLM is simply a little bit deterministic, randomly sampling on the vocabulary. So what we've shown here is that using this equivalence between LLM and Markov chain helps us to connect empirically demonstrated behavior in the literature with this Markov chain rich literature and theoretical literature. So it helps us to understand how different empirical parameters like the temperature, the context window, the vocabulary size acts on how you can use your LLM. But now we'll go into the main theoretical and empirical results of this work. That is, how do your LLM generalize to data not seen during the training? So using our equivalence, what we have now is that the generalization of the LLM is its ability to correctly approximate the transition between the states. So again, the states are sequences of tokens. So we predict the probability of transitioning from one sequence to another one, thanks to our LLM, but we have a ground truth probability of transitioning from I am the to I am the danger that depends on the true probability of language. So of course, we don't have access to the ground truth, but still we can do some theoretical work to better understand this generalization. And I will explain why it's difficult. So what you all know is that we have huge and increasing amount of training data for LLM. But actually, if you compare to the number of entries you need to approximate into this big transition matrix, it's really, really small. And this is why it's a very difficult problem. Again, for GPT-3, you have approximately 10 to the power 11 training tokens, but you have more than 10 to the power 10,000 entries to approximate. So in terms of statistical learning, it's really an under-parameterized problem, and it's very, very, very difficult. Yet, LLMs manage to do it. They are improving as we speak in terms of their generalization capabilities. So seeing this Markov chain perspective, the question we may ask is, how much training data do I need to be close to the ground truth transition of language? And more precisely, if I fix a level of error, let's say I want to be epsilon close to the ground truth, how much pre-training tokens do I need to do that? And more importantly, how much does this number depends on the model's parameters, like the hidden size of your models, the number of layers, the vocabulary size, the context window. And what we've demonstrated in the paper, so again, it's a little bit ugly, but what we've demonstrated is that if you take more than this n star training tokens, you have with high probability, you will be epsilon close to the ground truth. So here what we see is that the number of tokens needed to be epsilon close depends on two parameters mostly. Of course, it depends on the level of error, because the higher the error I authorize to have, well, less tokens I need. And it also depends on a constant B bar that depends on the model and the data parameters. When I mean data is how dependent and interconnected our training tokens are. Because again, we are mentioning tokens and in natural language, so we don't have the usual statistical learning independence between the data points. So I don't dig into the details, and I invite you to look at the proof, but the nice thing about this bound is that actually we can have some information in terms of the practical behavior of LLMs. And more importantly, this B bar constant directly depends on the vocabulary size, the context window, and the hidden dimension of your LLM. And if you recall, closely, each of your LLM is characterized by that. So if you consider the number of training data that was actually used to pre-train your LLM, and that is reported in the famous technical reports, you can compute the level of error, epsilon. And the question we ask is, do we have a correlation between the approximation error predicted by our theory and the practical error the LLM are doing? And the answer is yes. If you consider the Llama and Gemma models and recover the information from their technical reports, you can compute this approximation error predicted by our theory, and you compare it to their MMLU performance, which is a well-known benchmark for language understanding. And what you can see is that you have a good ranking and correlation, actually very high in terms of Spearman coefficient, between the theory and the practice. The larger our theory predicts the error, the worse the real performance is. Another very interesting phenomenon we observe is that we have distinct behavior between the different model families. And the reason for that is that our bound takes into account the model parameters, the dependency on data, the vocabulary size. And for instance, between the Gemma and Llama model, you don't have the same hidden dimension, the same number of training tokens, the same vocabulary size. But still, you have the proper correlation between the theory and the practice. Why it might be of interest? Let's say you want to design a novel model and you know the number of training tokens you have, so you can fix the training token, the vocabulary size, and you wonder what is the optimal or at least some plausible hidden dimension that you should use, or the context window that you should use. Well, thanks to our theory, providing you fix the other parameters, you could determine for a given approximation error you want. So here, as it correlates to the MMLU performance, you could fix some objective and determine the optimal hidden dimension. And we hope that practitioners might be helped with this in their LLM modeling design. So all of that is quite nice. We're happy. So before going to the next part, from just a technical perspective, to obtain this result, which is what we call the sample complexity in terms of statistical learning, it's used by deriving a novel generalization bound on the pre-training of large language models. So I don't dig into the detail of generalization bounds. What you need to keep in mind is that it's already very hard to do it from a classical statistical learning point of view. It's even harder for large language models for two reasons. First, you don't have you have dependent training data, not like the usual empirical risk minimization, and you have deep neural network that are gigantic. So it's really, really hard to control that. And we managed to obtain this generalization bound because we have this equivalent Markov chain perspective. So again, I don't dig into all the details, but we need to modelize, to model how dependent the training data are, because they are not independent. So we have some assumptions that are way more general than what is usually done in the literature. And then we follow by deriving the so-called generalization bound, where you just want to bound basically the gap between the true error and the empirical error. And hopefully it depends, as it's the case here, with our model and data dependent constant and the number of training tokens. So again, we're quite happy with our results. The only hard stuff is that for pre-training, you don't have access to the data, or at least I don't. Maybe companies have. Most of the state-of-the-art models, and even the Llama and the Gemma that are open source, you don't have access to the training data, which means, and you cannot compute this true probability distribution. So what we want to do is to go to the in-context learning part, where we can model this the data we generate, so to have the real ground truth and see how well our LLM behaves on that to approximate this ground truth transition matrix. So just briefly to give some context for the in-context learning part, basically it's the ability of a model to learn and increase its performance when it's shown some examples without needing to retrain in or update its parameters. So for instance, in NLP, if you want to do some translation, you could feed your LLM with good translation, some examples. So for instance, from English to French, you have apple, pomme, pear, poire, and then you give it the prompt and the answer you want to obtain, which would be cerise. And what people have shown in the literature is that you have increased capabilities and performance when you're doing this so-called in-context learning. So here in our case, we will take as input data Markov chains, because we have access to the ground truth transition matrix, and we will see how well our LLM approximates this ground truth. And it's quite interesting because it's not as costly as, of course, LLM pre-training, and we have access to the ground truth. So just really brief to give some context, we will compare the performance of our model with the current state-of-the-art in the Markov chain literature, which is simply the frequentist approach. So what it does to estimate the ground truth probability of transitioning from one state to another is simply to count the observations of the different states. In our case, the LLM method that I presented above is simply this equivalent Markov chain where we simply recover the next token probability to obtain our transition matrix. And we will see how well this LLM estimated Markov chain approximates the ground truth. So as I explained for the in-context learning part, we have the setup where the input are Markov chains. So we know the ground truth transition matrix between the different states. We have, of course, the state space is, so you could, for instance, think of about some random walks, so Markov chain. We have some parameters, so I don't dig into the detail of that, but the mixing time basically captures the dependency of the different states and how fast it can converge to the stationary distribution of the Markov chain. And basically what we did is to extend our previous generalization bound to the in-context learning part, where we have, again, the test error, so the generalization gap. We have the dependency with the number of in-context learning token and the dimension of the states. And we have another term here that's quite interesting, this distribution shift, which is simply here to take into account the fact that the input data we are using here are Markov chains, while the training data were natural language data. So you need to take into account this shift into your bound. And once we've extended this result, we can again compute the so-called sample complexity, but more importantly, we can derive in-context scaling laws, which tells us how the approximation error between the ground truth transition matrix of the input data and what our LLM is predicting with the evolution of the length of those Markov chains, the number of random variables in our Markov chains. And what we've seen theoretically is that we have a 1 over square root of n dependency, and actually it's met with practice. More importantly, what we see is that the dependency in the number in the context length matches the theory. And also we have that the more recent the model is, the closer it is to our theoretical results, which makes sense because the more modern and recent the model is, the smaller this distribution shift term is. And then we did some experiment to better understand the different variables in the bound. And what we managed to show is that the theory is matched by the practice with, again, state-of-the-art open source models. So we've tested with the Llama, the Mistral models, and again, the Gemma suite of models. And finally, you saw that you have this dependency in terms of the number of states of your Markov chain. And actually, when we compare to the frequentist method, we obtain that our LLM is way more robust and better with the increasing number of states compared to the state-of-the-art in Markov chain literature. So using, again, this equivalent Markov chain perspective, not only help us to understand the generalization and dynamics of LLMs, but it also enables to approximate the transition matrix of Markov chains, which in the literature is really a hard theoretical problem. So just as a take-home message to conclude, what we've done here is that we've obtained some explicit characterization of the inference mechanism in large language models by showing that it can equivalently be seen as a finite state Markov chain. So again, as I said before, the state space is gigantic, but it's finite. So it enables you to have access to the different rows and to connect it to well-known phenomenon in the LLM literature. And speaking about that, we've managed to characterize the different properties of this equivalent Markov chain, notably in terms of stationary distribution, the impact of the context window, the impact of the sampling temperature. And very interesting, at least in my opinion, I hope you agree, is that you can use those results, those purely theoretical results, to better understand some phenomenon and patterns that have been seen in LLMs. And last but not least, we've obtained generalization bounds on both the pre-training and the in-context learning phases, which enabled us to show that the theory is matched and correctly predicts the practical behavior of, again, state-of-the-art open source models like Llama, Gemma, Mistral, and even the most recent Llama 3.2 models. So if you're interested to know more about globally the paper, but also to look at the proofs, I invite you to look at the paper. And if you want to know more about my research, you can check out my website. And before leaving the floor, some just shameless self-promotion. If you're interested into the training dynamics, optimization, and transformers, we've done a recent work to better understand what is happening inside of your model during the training. So it's basically a visual sandbox that helps us to observe the evolution of each layer inside of your transformer. For the moment, it's for small dimensional transformers. And the nice thing is that it enables us to have some mechanistic interpretability on transformers and to connect it to some well-known phenomenon in the training dynamics. So you have the paper and the code here. It's work done with friends at Meta. Don't hesitate to take a look. And I thank you for your attention.